All right, this is Michael Piero, and this is part 2 of the final project where we're going to do a CFD analysis of a rectangular wing in ANSYS Fluent, given these dimensions from angle of attack 0, 5, 10, 15, and 20. But for this case, I'm just going to show 10 degrees angle of attack. And we also need to get the drag and lift coefficients using ANSYS and the 3D streamlines over the wing. So the first thing we're going to have to do is create our wing. Me personally, I like to use Solidworks because that's what I'm familiar with CADing software. So to make it in Solidworks, first we need to download the Clarky coordinates right here. We will save them as a text file, just like this. And we will open up the text file. And this is the wrong airfoil coordinates. We need Clark Y right here. Oh, Clark B. Here, that was Clark Y. That was Clark YX. Okay. Now we can open up the text file. And we will delete this information right here. And we need to select all of these coordinates, copy them, and put them into Excel, just like this. And as you can see, it separated them into columns already. If not, you will need to separate them into separate columns using Excel. And we will go ahead. And what we need to do to make this compatible for SolidWorks is we need to flip these coordinates right here. And the easiest way to do that is to actually number all of these lines right here down to where we're going to be flipping it. And then we will highlight all of this. And we're going to sort it from sort by column D. Right now it's the smallest to largest, so we will go largest to smallest. Okay, and now all these coordinates are flipped into what we like. And also we're going to get these, actually let's delete these extra zeros. And bring this up. So now everything's looking really nice for SolidWorks. And we just need to add in this last column of zeros. This is the Z coordinate file. So we add all these for our 2D airfoil, just like that. And now all of our coordinates are set and ready for SolidWorks. So we will copy all of them and replace them in this text file. Just have to make sure that the zeros right here are in line with all the others, just like that. And save. Now we'll open SolidWorks and create a new part right here. All right, and we're going to make sure, first we have to make sure, but before I go any further, if we use these coordinates, we will end up with a chord length of 1 meter. But for this project, we need to use a chord length of 0.3 meters. So we need to scale these coordinates, and by doing that, we're going to times them by 0.3, and that'll give us our chord length of 0.3. So times by 0.3. And we're just going to go all the way down with it. Just like that. And we'll do the same thing for the other column. Times by 0.3. And bring them all the way down. And then we just need to add in the zeros right here. And I'm going to replace the text file with these new coordinates. Not there was anything wrong with the previous coordinates, but we just want a chord length of 0.3 meters instead of 1. So, and just like that, and save this file. Okay. Now we can put it into meters, or whatever distance you need to use, and insert a curve through XYZ points. And we will search a text file for the one that we just made. And you should see a preview of your airfoil. If not, then you just have to go double check that your coordinates look all correct. And we'll click OK. This is our curve. If you look from the z-axis, it is normal to it, which means that we're in 2D. So we're going to sketch on the front plane and convert the entities of the curve to a sketch, just like so. One thing to note is if you look at the base of the trailing edge of the airfoil right here is not connected, so we're gonna have to connect to that. And you don't just want to draw a straight line, that would be incorrect. So we're gonna do a tangent arc through these points, and that'll connect our airfoil. Now we can double check that we have the chord length that we want by taking this distance, and you can see right here that our chord length is actually 0.3 meters, which is exactly what we want. So we can continue on making our wing. So this is our sketch of the airfoil. We need a wingspan of 1.5 meters. So we're just going to extrude this wing 1.5 meters. And this will give us a nice rectangular wing, just like so. Everything is perfectly symmetric. So now we need to say we need to get a 5-degree angle of attack or 10-degree angle of attack. Well, we just have to go to Insert, Features, and we need to move or copy. And we're going to select the body to copy and rotate about the z-axis. So if we want, for this example, say negative 10 degrees, we'll put negative 10 degrees in the z-coordinate. This computer is running very slow. Negative 10. And as you can see, our wing is now tilted up 10 degrees. So we can go ahead and click OK. And our wing is now at an angle of attack of 10 degrees. It's important that a problem I encountered while trying to do this project was when I was doing this feature, it would sometimes rotate it in other directions in the X and Y without me knowing, and I would have to come back and edit it because it would mess things up later on in ANSYS. So everything is perfectly normal right here. So now we need to save this part and open it up in ANSYS, and I've already done that. So I will go right here to ANSYS and we'll start Fluent and insert the geometry that we just made. Import. I'm doing 10 degrees angle of attack. It's the one we just made. Now we need to go into the design modeler and edit this piece. Okay, with design model open, we will generate our part. And here's our wing directly at 10 degrees angle of attack. So we need to get this so that it's able for Fluent to do an analysis on it. So we need to create a rectangle over this that's big enough so that there's no turbulence from the walls. That's big enough. And you could be more precise by, giving distances from this wall to this airfoil and stuff, but we just need to, this is just a simple project. So now we need to extrude this the same distance as our wing, 1.5 meters, and generate. So now we can see we have two different shapes here, which is exactly what we want. And I'm going to rename, this was the first part, this is the wing part that we imported, and this solid part is the rectangle surrounding it. You can see here, solid wing. Now what we're going to do is we're going to create a Boolean. I'm not sure if that's pronounce it, but it's what it looks like. And we're going to use a subtract operation with the target body being the solid rectangle and the tool body being the wing. And what this is going to do, it's going to subtract one geometry from the other. And when we generate it, you'll see that now we have a hole in this block that is the exact wing that we just imported in so that we can do our analysis on it. So now we will open up mesh and we will mesh this and apply our boundary conditions. And here we go. The first thing I'm going to do is I'm going to name my surfaces. So select this and name this as the inlet. If my computer wants to load. And I'll do it the old-fashioned way. Named selection. Oops. Don't know why this isn't creating. Oh, this is still design modeler. I am sorry. All right, so now we're in mesh. It looks very similar sometimes. Go ahead and put this right here. So now we will select the face and we will have our inlet right here, inlet flow and the outlet flow. And these four surfaces will be like a wall almost. So we'll just call it a wall. And lastly, one of the most important parts is to this section that we cut out, we need to name it our wing. So now we have our name selections. We can go ahead and mesh this. And what's nice about this is we only have technically one part, so there's not a bunch of meshing we need to do. Unfortunately, I have the student version of ANSYS, so my element size needs to not be that accurate, or else I won't be able to load it into Fluent, and I'll get a bunch of errors, which is why I'm choosing 0.6. And I already failed it a bunch of times trying to use other ones. So we'll use 0.6 as the element size and generate the mesh. It should be very quick because it's not that accurate, as you can see. But I can't choose anything lower or else I won't even be able to run it. So now with our mesh done, going to update it in Workbench. Now that it's done updating, we can open Fluent now. And here is our part all meshed and created with our inlet and outlet. It's upside down. Okay. And our wing is directly in the center here, away from the walls so that any boundary layer effects can be ignored. I'm going to use the K epsilon viscous model with enhanced wall treatment and pressure gradient effects. You can choose whatever one you want, but that's what I choose. Materials is air, and let's make sure that we have it selected. We're going to set our inlet velocity. Right here. And I'm going, for this project, this is the inlet velocity we'll be using. And now we need to set our reference values. This is very important that we compute it from the inlet. And you'll see all the information pop up. And we need to add our drag and lift coefficients to be analyzed. So we'll select the wing that we named earlier and select drag coefficient and click OK. We will also do that same exact thing for the lift coefficient. Select lift coefficient for the wing and select OK. And now we can initialize. We're going to do the hybrid initialization, except we're going to do 25 iterations, and we'll initialize that. And lastly, we will run the calculation. 100 iterations is good for this project. So we'll do 100 and calculate. And you will know if you did something crazy, if you start getting, coefficients of lift coefficients that are, absurd. So you can check that kind of while it's running. All right, with the calculation complete, these are CL and CD curves, but this is just for over the iteration, not really. This kind of shows you how it iterates to the point. But so we need to get our lift and drag coefficients. We can do that by going up to report definitions, and you can double click it. And this was our lift coefficient. We just click compute, click it again to get it pop up in. And this is the lift coefficient that we got for our wing. And for our drag coefficient, we'll do the same thing. And here's our drag coefficient. And the last thing we need to create the velocity vectors. So we'll go to vectors, velocity, and select our wing, and we'll display. And here's our wing angled at 10 degrees, and you can see the velocity, flowing over it. You can expect, this is kind of what we expect at an angle of attack of 10 degrees, that velocity is a lot higher on the top side of the airfoil and a lot lower on the bottom side, which will create that adverse pressure gradient. And that is our project.